This week we are going to start the experiment number 6. Okay. Force convection over heated horizontal cylinder or vertical flat plate. So we have the two applications, one heated horizontal cylinder and another vertical flat plate. So we have two different equipment and we will make two groups and we will do this experiment. Now, the objective of our experiment, everything depends on the objective. First, you know the objective, then we can write the complete report. So first, our objective is to find out heat transfer coefficient over a horizontal cylinder slash vertical flat plate by a force convection. Number 2, to compare H empirical and H experimental. So experimental, it is by Newton's law of cooling, and H empirical by using correlations and a dimensionless heat transfer numbers. So we can add one also to study various dimensionless numbers for force convection. Now we have two machines, as I explained, equipment description and specification. We have heat transfer unit and which is combined with a convection and radiation accessory by ARMFIELD, and another we have by GUNT. So we'll make two groups, one for ARMFIELD and one for GUNT. So
today we are going to do the force convection, and we have two types of machine. One is a GUNT and one is ARMFIELD. Like free convection, but we did there, and force convection here. Now we can do anyone, anywhere. Okay, so today we will make a group. So you 4 students on the GUNT and you 3 students on the ARMFIELD. Okay, so there is a observation table for horizontal cylinder on ARMFIELD and vertical plate on the GUNT. So we have to record the readings and then the simple calculation procedure that I will explain it. Now first we start it and we have to wait for the steady state. Okay, so there is a back switch as I explained last week. So make this black switch on. Then we need to adjust the power. So now in pre-convection we change the power, 60, 80, 100. Now here we'll keep the power constant. So we'll keep the power constant 80 watt. Okay, and we'll start the fan and we can change the velocity. Now the fan is, somebody keep it here. Okay, so this is a fan anemometer where we can measure the velocity and we can change the velocity from here. So this is a fan speed, we can change speed so that we can measure the velocity here. So what we need to measure from here, we need to measure TA and TH. TA and TH, then adjust the power to 80 watt and vary the velocity. First reading, second reading, third reading from the velocity. So whatever display here, record, because it is not stable. So when you record readings, whatever here you can write. So I will suggest what is the maximum velocity now. So first I will adjust the power immediately, very fast. So this is, make this switch on, like this, it is on, and now adjust the power to 80. So 15, 59, yes, this is power 80. Now it will heat up to a 90, 91, because yesterday I did the experiment and the temperature will be above 90. Okay, then above 90 with the velocity, some particular velocity. If you less velocity, then temperature will be high. If more velocity, the temperature will be less. Okay, so I will adjust the velocity now. So first make the fan on. Okay, then increase the fan speed. You can see the maximum velocity is 3.9 something. So I need 3 velocities. So I can make 1.5, 2, 3, or 3.7, 3, 2. Okay, I can adjust whatever I want. So I will try to adjust with the last reading. So I will make it 1.7, first reading 1.7, second reading 2.5, and third reading the maximum this. Okay, now I will adjust this from here 1.7. 1.73, because yesterday I record, I want to check today whether it will achieve the same temperature. Okay, so 1.7375, whatever it is there, we will write when we record the temperature. Okay, now TA is this atmospheric air temperature. See, if I put the head, then velocity will change because the Hawa is going from here. Okay, so this temperature I can measure as 22.9, and then power I can record here 81 or 80 whatever, and this temperature I need to measure. I will press it and I will measure after steady state reach. Okay, so when it's steady state reach, I will record, and then I will change the velocity to 2.5. Then I will wait for some time, then record same. Then I will make the velocity last 3.7 something, and I will record the readings. Understand? Now we'll continue to the arm field. So in exam you will get any one machine. So now here, come this side. So here this is a horizontal cylinder I explained. So this is a thermocouple which will give you the TH, yes, that is T10, and T9 is TA. Okay. Now here I need to adjust the power. No power now, voltage and current is a constant now. So I will adjust the voltage to 9 volt, measure current, I can calculate power. Then I need to change the velocity from here. So make the switch on. Yes, 3 switches. Yes, then main switch on. Then adjust the voltage to 9 volt. Is it on voltage?
Yes.
Yes. Now adjust to 9 volt. 9. Okay, 9. Then we need to measure the current. Not now, after, when we record the temperature. Okay, now this is 9 volt. Then near now, can you see here UA? Can you see UA? I need to keep this on UA. What is UA? U for velocity, A for air. Now what is the UA?
Velocity,
Yes.
air.
No, this UA,
yeah, velocity
for air, and this
F
water,
for-
there is no water.
Okay, no water.
W for water, FW for water, there is no water, only air. Okay, so I can measure the speed of air from here. Now how I can measure? So this is a velocity measurement. This question asked in interview, how you measure the velocity?
By density.
No instrument. How you measure the velocity? There is a ano, like thermometer, thermocouple, or temperature. Like velocity, there is a aminometer. Velocity sensor is connected here. See this, there is a clip. There is a clip here. So I can press this and I can connect here. So where I have to connect? UA means UA.
Velocity.
Yes, so it will give you the velocity. If you connect here, no, wrong. Okay, so it is always connected here, nobody will plug. So like
The
this.
difference will be the reading.
Yes,
will be
because
different.
this is for water, this is, there is nothing. Okay, so this is a service unit. So which service you want? We want velocity of air, so I connected there. So this cable is connected to UA, and keep this on UA, start the fan. Okay, and now velocity is 0. Now open this, now I can increase, and now I can keep this velocity 5, 7, 8, or 5, 6, 7, whatever. So first I will check what is the maximum, and then I can see. So I will open this. 8 is maximum. So I can choose 5, 6, 7, or last is 8. So I can make adjust first on 5. So close means decrease velocity. So I can adjust this to 5, and I will wait for steady state.
No, you will create it. Okay. Okay.
Okay, whatever number I will write that. Okay, so now I need to keep this on T. This is T9, TA. This is T9. Okay, now I need to keep it on T10, and then when this temperature stop increasing for 1 minute, I will record. Okay, now next I will make the 6, wait for steady state, record the temperature, and then 7 velocity. So power is constant now.
We have for ARMFIELD, group number ARMFIELD and GUNT. So those who are having GUNT and those who are having ARMFIELD, they will write respective diagrams, and another is a GUNT. The same procedure, same calculation, only applications are going to change. So in experimental setup, we have the horizontal cylinder. So this is a vertical pipe, and here is also a square pipe for GUNT. In the pipe there is a horizontal cylinder here, which is kept horizontal and having a heater this side. So electric current will flow through this heater and it will become heat, so we can measure voltage and current will get Q. Same here, there is a vertical plate. So same here is a vertical plate and it is connected with the electric heater, and directly we will get Q here. We can measure the Q from the machine, and here we need to calculate Q. So this is a vertical plate and this is a horizontal plate. So the dimension of the vertical plate and horizontal plate, it is given, this is 0.07, and the diameter of this, it is a circular in section, so diameter D is equal to 0.01 meter, and here the dimension is given as 0.12 and 0.12 height and length. So here there is a thermocouple which is used to measure the TA, and here there is a thermocouple which is give you TH. Same here, we need to press the sensor here and we can measure the temperature TH, and there is another thermocouple TA, and there is also another temperature here, so we are not interested in that temperature, so we can measure TA and TH here. So here our observation is to measure voltage, current, temperature TH and temperature TA. Here in GUNT, our objective is to measure temperature TH and TA and direct QW in watt. So there is a fan here. There is a fan here. So when you start the fan, the air is forced over this horizontal cylinder, and also here there is a fan and the air is forced over the vertical plate. Now due to the fan, the air is forced, means it is having velocity, so we have to change the velocity. So this is another variable. Here also we have the velocity, so we are varying the velocity 1, 2, 3, and we can measure the temperature TA and TH, and we can measure the. So our observation table consists of first voltage, current, and then velocity, and then TH and TA. So same here. So here our controlling parameter is a velocity. Now when air flows over the horizontal cylinder, so if you see from side, it looks a circle. Horizontal cylinder is looks like a circle, and the air is flowing like with a velocity v. So this air will become hot and it will go up like this. So we'll find a like this boundary layer. We'll find here like this boundary layer. So this is a boundary layer separation as hot air moves out and the air is moving up. So the effective heat transferring length is this, and it is diameter d. So when you find, now here it is a velocity is concerned, that's why we need to find a Reynolds number, and Reynolds number is rho v d by mu. So depends on r vd by nu, whether mu and rho is given or nu is given. So here d is the effective length, heat transferring length, so we need to take d. So in case of vertical flat plate, so there is a fan, so air will move like this with a velocity v. So then the hot air, this air will become hot, and this hot air will go like boundary layer will be created here. So due to this, hot air goes out. So here we need to consider this length. Maybe L is equal to, this is Y and this is X. So Y is 0.12 and X is also 0.12. In the lab manual, L is given as X plus Y by 2, so it is 0.12. But this is not true. This is not true. So we have to take L. In Reynolds number, we have to take rho V L by mu, where L is the effective length and it is 0.12. And in lab manual, it is given as a, take average. So 0.12 and 0.12 average is 0.1. So this formula will get the same answer, and by this rule we will get the same answer. But remember, we have to consider this L. This is a square plate, That's why we are getting L same. But if it is a rectangular plate, the L will be different and your answer will be wrong. So here important is you need to consider this L as distance Y and what is the height of that. Now, in sample calculation, my flow chart, what I will find? I will find Q first by Newton's law of cooling. Q is equal to HA delta T, TH minus TA. So this is my objective. So this is by experimental. TH is known, TA is known, Q is known from the equipment. Where area? Now where area is equal to pi dl. Heat transferring area. Heat transferring area. This area into the perimeter. Circular perimeter. So this is a perimeter and this is L. Pi d into L. Okay, for cylinder. And here the area will be here and the area will be xy. So this is the difference. So once we know area, we can find out the heat transfer coefficient. H experimental is equal to Q by A TH minus TA. Okay, so this is by experimental. Now by empirical, we need to find out all the numbers. First number is a Reynolds number because of force convection, the Reynolds number. In last week we study a free convection where we study a Grashof number. Now Reynolds number is equal to Re is equal to rho V d by mu. This d or L for flat plate or for cylinder. So this is the first number we need to find out. As there is a velocity, as there is a force convection, there is a velocity, and due to the velocity, we need to find the Reynolds number. Number 2 is a Prandtl number. Again, it is a property, mu Cp by K. All these are property, hence this is a property. So this Prandtl number may be available in the table. If it is not available, we can take a Cp, mu, and K. We can find out Prandtl number. Now these two numbers are related by the correlation, and that correlation is given to you, and that correlation you will find in lab manual. As you know the Reynolds number and Prandtl number, we need to choose, depends on the Reynolds number, we need to choose C and M. Put the C and M here, so we can find out this by this equation. So I will show you, depends on the two. These two numbers are related by the Nusselt number. Third number is a Nusselt number and it is denoted by Nu and it is nothing but Hd by K or HL by K. So this is D for diameter. So here we use capital D. So we'll use capital D. So Hd by K and diameter is given. K is a property. Nusselt number we can find by this relation for vertical plate and both our relations are same. So there is no change. So Nusselt number for diameter Hd by K, HL by K. So we can find out the Nusselt number and then we can find out H from this equation. H empirical is equal to Nusselt number into K by D or L. So our objective is to find out experimental, empirical and experimental. The same procedure last week we used. Now let us will start the experiment and we'll record the readings. Experimental procedure we can write from the what you did. Then result and discussion. So if you want you can write both of them or you can write only one. It is up to you. For ARMFIELD we can write for horizontal cylinder. Horizontal cylinder diameter is equal to 0.01 meter. Length is equal to 0.07 meter. And for vertical plate you can write x is equal to y is equal to 0.12 meter. Okay, so this is the observation given to you. And number 2, properties of air and correlations or empirical relations from data book, from heat transfer data book. So these are the given to you for observation. Now observation table will transfer the readings. For 9 volt, here we are going to keep the voltage constant and we are varying the velocity of air. So let us take the readings for horizontal cylinder.
Tell me TH. What is TH?
89.
89. Next.
They move it to T9, right?
T9, yes. TA. How much TA?
21.5. 0.5.
Yes. Now change the velocity to
7, right?
6.5.
Because here we talk at 6.
We will take here only. 6.5 adjust. We can check both same or not. Yes, good. Okay, now we will wait for an.
Now we
6 point velocity, how much?
velocity is 6.5. 6.52. The
TH,
T out.
yeah, TH.
T10 82. 82. And
T9, TA.
to 21.7. 7. 7. 7.
And this is the velocity to 7.5. We will wait for. Now keep this on T10.
T10.
So T8 78 and T9 22.1. Now we'll make the voltage 0 and we'll switch off. The voltage 0, then switch off fan. For vertical flat plate, what is the power?
The power is
80,
81.
81.
Yes.
Now velocity is how much?
Velocity is
1.78.
1.78.
78. What is TH? Now press it by hand.
Huh?
Press up by hand. Yes. And check how much.
90.
90.
90, yeah.
90. What is TA?
TA, where is it? TA is 23.
23.3.
0.3. Yeah.
Now
So-
increase the velocity. This
This
second. Yeah. First one.
First one? This TA,
23,
okay.
yeah. And velocity, increase the velocity to 2.5 around. No power, 81 power.
Around 2.5 around.
Do the calculation for first reading and then go. Okay, show me the first calculation and then go. So second reading, third reading we will record here. So last reading we can record it 78.4 and 3.54 velocity. The power is 82.
So for 9 volt, the current is 1.58, and you can calculate Q. In sample calculation, you can transfer the value here, and then velocity of the year. We can keep it first 5 meter per second. So unit is meter per second. So this is volt, this is ampere, and Q is in watt. First 5.5 and 8.5 meter per second. So we'll keep this velocity and we'll record 71, 64, and 57. And the outside temperature is 24.1, 22.9, 22.1. Yes, now we can calculate the delta T and whatever all the calculations we will do here and we will write. So we'll do the sample calculation. So calculation number 1, heat flow is equal to Q is equal to voltage into current is equal to 13.32 watt. And for GUNT, you can take directly Q is equal to dash watt. Okay, for GUNT. Now number 2, the heat transferring area. So this is in the table, that's why I wrote number. So area no need in table, so we'll write heat transferring area is equal to A. A is equal to, so this is a cylinder and this is diameter D and this is L So heat is transferred from all these cylinders. So we need to take pi del. Answer is 2.1991 into 10 to the power minus 3 meter square. For flat plate, area is equal to xy. Area is equal to 0.12 into 0.12 is equal to 0.0144 meter square. Number 2, heat transfer coefficient by Newton's law of cooling is given by Q is equal to HA TH minus TA. So here we know Q, here we know area, here we know TH, and TA we can find out H, and that is called experimental. H experiment is equal to Q by A into TH minus TA. So I will write for the GUNT and ARMFIELD. H experimental is equal to 26.44 watt per meter square degree centigrade or Kelvin. So here also put the directly Q and area and TH, you will get experimental. Number 3, properties of air at T average is equal to TH plus TA by 2. So put the values, go to the table and find out the properties. Our temperature is lies between, so we can write the density, it is average. So your temperature is an average 320 around, it is an in between. So we'll take the properties at an average or by interpolation. So by interpolation we can write the properties. So we'll write the properties of air at 320 Kelvin. The density is equal to 1.100 kilogram per meter cube. Then Prandtl number is 0.710. Thermal conductivity K is equal to 0.0277 watt per meter Kelvin. And kinematic viscosity is equal to 17.94 into 10 to the power minus 6 meter square per second. So once we know the property, we can find out the number. The first number, the important number, is a Reynolds number. Re is equal to rho Vd by mu. Or here I don't know mu, I have mu, so rho by mu by rho. If you take rho down, it will be a mu by rho, it will be a nu. So Vd by nu, this is for cylinder, and for flat plate it is VL by nu. 2787.07. So similarly calculate for vertical plate, put the velocity which is given to you, length is 0.12 and nu from table, you can calculate this. Once you know the Reynolds number, go to the table. From this table, find out C and M. So Reynolds number is near about in between this. So we can write the C and N as 0.683 and 0.466. From given table, choose C and M at Re is equal to 2787.07. So C is equal to 0.683 and M is equal to 0.466. By correlation or empirical relation, Nusselt number is equal to C, Reynolds number is to M, Prandtl number is raised to 1 by 3. This is given for horizontal cylinder and for vertical flat plate. And it is 24.563, and it is nothing but HD by K or HL by K. So we can find out H, and that H is called H is equal to H empirical. It is a empirical is equal to Nusselt number into K by T. So H is equal to 68.039 watt per meter square degree centigrade or Kelvin. So this is the H empirical. So similarly, you can calculate for the flat plate. Now conclusion number 1, heat transfer coefficient by experimentation and empirical. Empirical is Exp is equal to 126.44 watt per meter square degree centigrade or Kelvin, and H empirical is equal to 68.039 watt per meter square degree centigrade. So what is the difference? What is the relation between these two? Number 2, I can write H experimental is twice H empirical. So this is called local heat transfer coefficient is double. So this is the conclusion.